This is Geometry Section 10.3 on arcs and chords. And we're going to start by looking at a few theorems first. And the first one, if a diameter is perpendicular to a chord, so here is my chord, and if I have a diameter that is perpendicular to it, then what can I say? Then I can say that the diameter is also bisecting that chord, meaning this small little segment is congruent to that little segment as well. I could prove that by drawing in this radius and that radius. That gives me two congruent triangles, and then I could prove that those two little segments would have to be congruent to each other. Next, the perpendicular bisector of a chord. So here is my chord. I want to draw the perpendicular bisector of it, so I'm going to go through its midpoint. I want to make sure I'm perpendicular. And there is my perpendicular bisector. So since this green segment, this green chord, is a perpendicular bisector of that blue chord, what could I say about it? Well, it must pass through the center of the circle, and that makes it a diameter. Two chords are congruent if and only if they are equidistant from the center of the circle. In other words, if this orange chord is congruent to this yellow chord, that means that they're the same distance from the center. And with distance, it's implied that we're talking about the shortest distance, the perpendicular distance. So these two segments would have to be congruent to each other. Conversely, if these two chords are both equidistant from the center, so if these two blue segments are congruent to each other, then I would be able to prove that this yellow chord is congruent to this orange chord. So we have a biconditional here. Two chords are congruent if and only if they are equidistant from the center of the circle. Lastly, we're going to look at a problem. Points A, B, C, D, and E are all collinear. We have circle B, so B is the center of the circle on the left. We have circle D. D is the center of the circle on the right. The length of AC is 26. Now, as that applies to the little circle, that means that the diameter is 26, so the radius is 13. So this length AB is equal to 13, and any other radius would be equal to 13 as well. Another radius that we have is this blue segment BG, so BG is also equal to 13, as well as BC. GH is equal to 24, and since I have this segment, which is a diameter, perpendicular to that red chord, it also means it's bisecting that chord, and since the entire length of GH is 24, that means that this part of the segment is going to be equal to 12. Lastly, DE is equal to 16.9. That means that the radius of this circle on the right is equal to 16.9. I'm asked to find the length of segment DC. Well, I'm going to start by looking at this yellow triangle. And it is a right triangle. I now have the hypotenuse of 13. I have a leg of 12. I recognize that this is a Pythagorean triple, so this length is going to be equal to 5. And then since the entire radius of this circle is 13, and I have this much as 5, that leaves me with a length of 8 for that segment. Now I'm going to go over to the other circle, and I'll highlight that circle so it stands out a little bit more. We've already established that the radius of this circle is 16.9, so from point D to any point on the circle is a distance of 16.9. This turquoise segment is a radius of the circle. We've used up 5 plus 8, or 13, which means that there's 3.9 units left for the length of DC, so DC is exactly equal to 3.9. And then for GC, we can look at this right triangle, and with that right triangle we can use Pythagorean Theorem. 8 squared plus 12 squared is equal to GC squared, and 64 plus 144 equals GC squared. GC then is the square root of 208, and that is going to simplify down. If we divide that by 16, we get 13, so that means that this is going to be equal to 4 root 13 units.